Great, so what we're going to do today is really just one notebook, and that is going to be modeling of stress resultants. If you want to model a specific moment or a shear force or a normal force or a torsion on a finite element model, how do we go about modeling that so that we do it properly? That's really what this is going to be about. So what we're going to be focusing on is how do we do pure moment, how do we convert a pure moment into consistent nodal loads so that we get the response that we expect to see. Okay, so if we have a bar with only a pure moment, we expect to see no shear, no other stresses except for the sigma xx stress that we should see. How do we model it to as a matter of fact see that? So this is focusing on a moment, but this is related to any of these that's in this part of the stress resultant. So I'm going to be focusing on the bending pure moment because it's sort of something that you've done, I know, quite extensively in W27 when it comes to moments on beams, and now we could just visualize it, and it's an easy, nice visual check to see that, oh, are we inducing some shears that are unwanted or actually modeling it properly? Okay. So first off, we need to remind ourselves that the moment is the integral of the stress distribution across the surface. And so when we look at what we've learned from having a moment on an applied, we know that the stress distribution is essentially a linearly varying sigma xx stress component for this example here. Okay, we give this macroscopic or global coordinate system. That's what we know there. We need to model this with rollers so that there's Poisson's contraction, and there needs to be a point there that's also not moving in a y, so that this thing is not moving up and down. And essentially we only have horizontal stresses, that stress components that are non-zero are sigma xx that acts on this beam. Okay, that's really what we need to understand. So how do I model this in FEM? Well, in reality, the answer is on the right hand side. We need to model this with consistent nodal loads, this distribution of loading on an edge. So this is really the important step, that the link between the stress distribution and the bending moments, that is really what we need to be able to model, because in the end what we need to get to is model this stress distribution of this phase, convert that into consistent nodal loads. Okay, so first off, there's a couple of things that we need to just remind ourselves of. We need to first recall that body force load in 1D is similar to the load distributed of an H and 2D element. The implication is that the shape functions that we had for the body force was sort of the N1, N2, N3 shape functions in the 1D case, and then we multiplied by the appropriate body force. And so we had a total body force that we wanted to apply, total newtons that we wanted to apply as a body force over structure. That was maybe 1,000 newtons. That split was then essentially 1/6, 2/3, 1/6 for the left, middle, and right hand side nodes. And so that ratio of distribution for the total load over an edge or over an element stays the same for the 2D case when we have it load distributed over an edge. And I'm going to show you why that's the case more explicitly. I've already asked you to go and confirm that for yourself, that if you take the shape functions of the Q8 element, you substitute sort of the right hand edge in there, you see that you recover essentially the normal bar elements, 1D bar elements shape functions as a function of one of the variables, depending on which one you've substituted, which edge you're looking at. So I'm going to just explicitly demonstrate that so that we're comfortable with that. And all we need, the next thing we need to do is we need to be able to write this stress distribution over an element in its local coordinates. That's really what we need to be able to do. So make sure that, let's say if we have an element here and an element here, that if I evaluate at the right value for, let's call it eta on this edge, then I recover 0, and at the top I recover the maximum, and that in between is linearly varying. That's what we need to be able to do to be able to integrate and compute the consistent nodal loads. So this global distribution of stress, we have to then for each of the elements figure out what is the local variation of stress over that element, and then that essentially that total force over that element that we would have applied that would have been applied over the element will then split according to the consistent nodal loads. Okay, so this is not going to split 1/6, 2/3, 1/6 because this is not a uniformly distributed load. This is a linearly varying load, so we have to go and compute it. Okay, so the question is given a moment that it's 1 Newton meters, what is the consistent nodal loading? That's the question that we have. Okay, so I'm going to first show you how to do it inconsistently. So that's the first one we're going to look at, and then after that we're going to see how do we do it consistently. Okay. So the first question we do, make sure that we understand which stress to expect to see, what stresses should be 0 and which ones should be non-zero. So the only non-zero stress that I expect to see is sigma xx. No shear and no sigma yy should be acting here. So there should only be linearly varying sigma xx stress component. Okay, there's no shear, so there shouldn't be any shear component here. This is a pure bending moment that we're modeling here. Okay, so this is going to be the setup. 1 Newton meter moment applied here, 4 millimeter height, 8 millimeter long rollers here, clamped there. So this can have Poisson's contraction. There is essentially the structure that we have. Okay, so let's look at first at the inconsistent way of modeling this. So the first kind of stab that if you think about how to go about would be essentially to model it in maybe just having a force essentially here pushing and a force pulling here at the bottom. So pushing at the top and putting at the bottom, so that we have compression at the top and putting tension at the bottom. That's maybe the first kind of thing that one would imagine. So the question we have to ask ourselves, we want to have 1 Newton meter, what is the loading that we expect to see here? What is that sort of force that we would like to encounter? That we must be pushing and pulling so that we have a 1 Newton meter moment. Well, first off, we need to ask ourselves, what is this distance from here to here? And so that distance is essentially 2 millimeters. If this total distance is 4 millimeters, then that distance is 2 millimeters. So I can imagine that I have to, if I have a force here at pushing here at this side of, let's say, 250, and I multiply by 2, that is a moment there of 500. This one will be in the same direction, so then I have another 250 pulling here, a distance of 2 is another 500, so 500 by 500 Newton millimeters. Okay, so that's 1000 Newton millimeters, and that's the same as 1 Newton meter. Okay, so we expect to see a load of Newton of pushing here of 250 newtons and pulling at 250 newton, because that will then essentially be 1000 Newton millimeters, which is the same as 1 Newton millimeter, 1 Newton meter. Okay, that's what we need to make sure of. Okay, so essentially that's, you can go and make sure that you can confirm that for yourself. What is that load that we expect to see being applied there? So we can open up this file and make sure that that's indeed the case. So let me open this, load this file here quickly. So make sure that I can show you there's the structure. It's a height of 4 millimeter, 8 millimeters long. Here's element connectivity, boundary conditions. And here I've applied a 250 and a minus 250. So we can just make sure that it's at the right nodes. Be happy with that. So the top one is going to be in the negative direction. Top is, and that's at 37. So that's minus 250. And then I expect to see a pulling a positive at the bottom at 9 in the x direction. So 9 in the x direction of 250. Okay, and then in between here, I just I could have also deleted them. The 14, 23, 28, because they're just 0, the same as the rest ones. 14, 23, 28. I'm keeping them in here on purpose, so when we want to do, maybe if you want to modify this to do the consistent already, you can then start with this as a blank slate, and already the right nodes where we expect to see some values to occur is already in there. Okay, so that's important. That's really that aspect. Okay, so let's go and run this and see what we get out. What do we get? And we can just confirm that we're happy with the answers and just check what's going on. So let's see. So here I've got here essentially it looks like something that's a bending moment. I've got a magnification factor. We can make it maybe slightly larger. So we can make the magnification factor maybe 50. This doesn't change the answer, just says magnification factor. We do see some, so this is really just, it's looking like there's a moment there. So compression at the top, tension at the bottom. If I look at the von Mises stress, I can see here a nicely linear varying stress field as expected. But here I do see some, maybe some interesting, more interesting behavior than what I would expect it. We can ask ourselves, what is the stress that we would expect to see for that 1 Newton millimeter bending moment? So that's another question we can ask ourselves. If we look at this my over I, what should that sigma xx values be, the maximum sigma xx be? So it's 1 Newton meter. We've got multiplied by this y distance, which is essentially 2 millimeters divided by I, and those are all values that we need to make sure that we're comfortable that we can verify against that. So you can go and do the calculation. I'm going to do the calculation a bit later on just for you to check, but I want to give you a chance to just check if you can see what the answer should be. But it looks like if I look at here, I can see for the sigma xx at the top nice compression, at the bottom nice tension that I get down. I do see some deviations around here where I've have that pull push modeling, so it's not 100% just linearly varying. There's some action, some other stuff going on here. So it looks like ballpark around about 460. That's just now all in MPa. we should see here. Okay, so that's what we see from sigma xx. Sigma yy, I expect to see 0, so I do see 0 far away from where we did the model. That's far away, but look at, there's definitely some action close by. Look at that action close by. Look at that. So there's definitely a sigma yy non-zero component here. That's not ideal. And sigma xy, also a fairly large shear stress that's not ideal here. You can see that there's large variation what's going on far away. Shear stress essentially 0 as expected. Okay, so these are the things that make sense. So let's just first check what is the stress that we expect to see if you just do this calculation my over I. So that's now for a bar that is essentially, if you just go back to this input file, you can see its thickness is 1 millimeter. So that we can just calculate that quickly. So let me just quickly do this calculation here at the bottom. So I'm not going to do the equilibrium now, I'm just going to first just show you what stress we expect to see. So sigma xx is equal to m, which is 1 Newton meter, times y, which is going to be 2 millimeters. I'm just converting now to meters, divided by I, which is going to be 1/12, times a thickness of 1 divided by 1000 times height, total height of 4 millimeters by 1000 to the power 3. And then I can just print. This is going to be my stress in MPa. Oh, so this will be stress actually in Pascal. Because I'm converting everything, sorry. And this is Newton per meter, and this is now all meters. So this is going to be in our answer in essentially in normal pascals. Okay, so if I look at this, this is first 3, second 3, 375 MPa is what I expect to see. If I start looking at the answers here, what I'm seeing here, let me just go up. I essentially see von Mises stress is much larger here, so it's almost up to the 600s, and you're supposed to see something that's around about 375 MPa, because the other components are all 0. When I start looking at sigma xx here, I'm seeing here a maximum stress around about 460, and a compression also of minus 460, which is much larger than what expected. So this is why it's important that we do the verification, have a good ballpark of what we expect to see, so that we can interpret this result and see, okay, so we initially just by looking at the results saw a 460 sort of estimate of the maximum stress and sigma xx stress, but we see is that's much more than what we expect to see of 375 MPa. So this is much larger. So the stress here, you can see also this color stress there is much lower there. And so you can go and open up the input file and verify for yourself what the answers are there. But we get the answers out as a so this is essentially our, let's just go look at our input file. What's our element 1? Element 1 is 11317, 113, where's this? What's the node numbers? 131715, 131715. So that's sort of the bottom element. That's the first one. So let's just look at the first element. So element 1. We just look at that one's response. So you can easily check which element is this one here by just looking at the appropriate node numbering. So you should be able to confirm that for yourself. So making that link, that is important. Because let's just quickly check 131715. Let's just get that stress SXSIC out. So let me just plot that here. So that's going to be the stress at the at the node number 1, 2, 3, 4. And if I look at node number 1, 375, and that's essentially what that answer that we expect to see. That's on 375 MPa. Here's at 375 million Pascal, or 375 MPa as well. So you can see that that's really good in the ballpark of what we expect to see. That is now for this element right down here at node 1 of element 1. So I'm looking at this sigma xx. I'm looking at element 1, which is our first element, and at node 1. That's essentially element 1, node 1. Then it'd be node 1, 2, 3, 4 would be these values that we see here. 1, 2, 3, 4. Okay, so that's just make sure that we are clear with that, and we can see essentially that the sigma xx on this center, this neutral axis line almost there is essentially 0. It's close to 0. So that's a very small value, 0.4 and minus 0.2 MPa. Okay, so that's really cool to see. That's all good and well. I can also, if I wanted to check at this other element, so this is the one that's in tension, we can also look at the element that's at the top, this one here. So it's 15, 17, 31, 29, 15, 17. So 15, 17, 31, 29, that's element number 5, or the 4th index, but that's the 5th one down that list. So that's what we're going to be looking at. If I go down this list and say, what is this? The 5th one. 1, 2, 3, 4, 5. Okay, now we just need to look at, make sure that we look at the right element numbers. So that's for this element here, we have node number 1, 2, 3, 4. So that's 31, 29. It's 3 and 4. I'll show you. Node number 1, number 2, number 3, number 4. That's the node numbering in the local system. So that's 3 and 4. The 3rd and 4th position we should be looking at. So it's just a good recap of how everything's working again. So that's essentially 3rd and 4th one is this one. 3rd and 4th one, or 3rd and 4th one there. So that's what we see here. So that's beautiful. We see there essentially the intention, the same sort of minus 375 MPa. Beautiful. Okay, so all of that is working well. But when we start looking at what is the stress here, where we've applied this inconsistent loading, see what the time is. I almost have to finish here. Where we applied this inconsistent loading, let's just quickly look at that one. So this is essentially going to be the element with 21, 23 to 37, 35. 21, 23, 37, 35. So that's the last element. Okay, 21, 23, 37, 35. Let's look at that one. Again, we're going to look at the last two and see what their values are. This is going to be 37, 35, the last two values. So this is the last one we have to look at, and look at that. Much larger than minus 375, as we expect to see from our closed form solution for this pure bending moment. Can you see the consequence? All of a sudden we have a much larger stress locally because of this inconsistent modeling, by just pulling and pushing on this structure in this try-to-way to model a moment. Okay, so that's quite a significant fraction out. So that's really it's not really that small. So it's about, what is it? It's about 50 pascals on 375. So that's about how much we are out, or even more. It's about 60 pascals out on a value of 375. So that's the consequence if you don't do things inconsistently. We can't trust the values close by to where we did the model, but far away everything seems like Saint-Venant's principle looks hunky-dory. Okay, so I'm going to stop the video here, and then we'll start the next one, which will then look at the consistent node loading.